All right, so yeah, so this is going to be section 8, which is multiple linear regression. I'm just pulling up the resources right now. So like I think I mentioned just a second ago, that might not be updated on the repo right now. I'll make sure to update it by the end of today. Also know that the recordings from the past few days are now up on that playlist. You should be able to see those. So if you missed it or want to review those specific recordings, those are there. Also know, like, if you're going into this project, you can always go to the student resources, that spreadsheet and such, and see what other like instructors, if they do it. I think Raphael, maybe it's Jeff, either Jeff or Raphael, they probably both did it, but I know at least, I think it's Raphael, did an initial, like a start of the project and was saying, oh, like this is how you kind of start it through. It's like an hour-long recording, but he goes through like the first like initial part of like how this looks like and everything. So I think that's a really good one. So let me make sure. Yeah, so this is gonna be, okay. Yeah, I didn't have it here. So we'll get to that in a second. Okay. So I'm talking a little about myself. So, all right. So last time we talked about linear regression, and essentially linear regression is just our way to, what's it called? Is do our prediction. Sorry, everyone. There. Linear regression basically is our way to kind of like do a prediction. Basically, we have our different variables and such, and we have our variable, our independent variable or our feature, and we're trying to make our target. Our target is usually the y-axis, our feature is usually the x-axis. You basically get our little points. You saw the little scatter plot, and you basically draw our line of best fit. We can calculate that directly, and with that line, you can say, okay, this is our predicted of what it's doing. We can actually mathematically show that that is the best line to go through based on the residuals. Okay, so multiple linear regression is basically about the same stuff, just with more. Which with that more means that we also have to consider other aspects of the model itself. So I'm going to go share my screen for this notebook. And all right, Zoom likes to move my little window around when I share. Okay, so you guys see multiple linear regression here. All right, cool. So multiple linear regression, basics of it is that we're going to be using the same thing as linear regression, but we're doing it for multiple variables. Pretty straightforward, right? So you'll sometimes hear me and other people refer to this as multiple dimensions or multidimensional. So some typical imports that you'll probably use in general, I'm importing NumPy. I'll import pandas in here too. So if you have like, starting off this project, these are probably like the 4 main packages you'll use. You might use other ones that you find, or you might find other aspects. For example, OLS, which we'll talk about in a little bit. For stats models, you might have this, but at least these first 4 are pretty typical for pretty much any data science project. So good to have. So basically, instead of having like one variable and one target, we have multiple features and then one target. So the idea here is that we're taking all these features and predict one thing. So the best way to kind of show this is like a quick example. So this one right here, basically, this np random.seed, basically, I'm just generating it so it's not completely random. It just starts at the same spot, so I can generate the same random numbers. We'll go into this in the future, but basically just knows that that's what the seed's doing. And then this np.random uniform, basically I'm picking, was it 100? Is that right? Yeah, I'm taking 100. I'm making 100 different numbers between 18 and 65, and between 18 and 65, those are all equally likely. And then I'm just basically saying, okay, let's have sen. What did I put sen? I actually don't know what sen is. This is where comments would be useful, right? But basically, no, this is going to be our, I think this is our variable, and this is our feature. I'm sorry, this is our feature, and this is our target. So, okay. And then basically I'm doing the same thing, doing a random, creating a new random data set. So if I go ahead and plant this, oh, seniority, there we go. So seniority is our variable. Income is our target. And so I'm just going to go ahead and plot these out. And you can see here is I have this nice, beautiful scatter plot along with the actual line right here. And this is just a quick line through here. I just made this randomly. You might see it's like, it's not quite right. That's because it's not the line of best fit. So just kind of knows like, okay, this all kind of depends on exactly how you create this. But the point is that you'd probably have these things where you have your scatter point and your line trying to explain those data points. So our overall equation will look like something like a target is equal to a slope times a feature plus an intercept. That was our linear regression, our simple linear regression of just basically 2 dimensions, right? So if we wanted multiple ones, what we can do is we still have our intercept, which I'll call w0, and then we have our other feature x1, and I'll say times it by some weight, the slope, and then another slope, a different number, times x2, all the way through xn. So basically, it means that I'm just doing a bunch of little linear regressions all together. You can kind of see that this basically comes through. And this is where this W, you'll see me use this, you'll see other people use it. Part of the reason why is because for other machine learning algorithms, you might call these weights. And they're also kind of useful. You can do like vectorization with this. So that's why you'll sometimes see this reference. But to make like a 3-dimensional plot, then if I had 3 graphs, and this is just to show you what this looks like, basically, excuse me, instead of having a single line going through in 2 dimensions, we actually have a 3-dimensional plane for 3 dimensions. If we had a 4D, like if we had 4 features, in that case, we would, or sorry, 3 features and 1 target, you would have a 4-dimensional graph with a 3D object essentially being like the cross section. So it'd be like a hyperplane essentially. And so know that it gets more and more complicated, but the important part here is that the shape itself, this linear regression line, this multiple linear regression line, isn't really a line. It's really like another higher dimensional shape. But what is nice about this is that if you imagine like a sheet of paper, like it's kind of floating in space, if you looked at it, so it's just like exactly, oh, I have a piece of paper here, a Joanne's coupon. Okay, so if you have like a piece of paper and you looked at it straight on, it looks like a line just going right through here. And then if you looked at it straight on going from this direction, you would see another line going this way. So you can basically think of it as like a bunch of linear regression lines all put together. Now, the caveat to that is that you're not making a linear regression line for each individual variable in the target. You are basically making that regression line considering all of the variables and making the best fitting line between all of it. So some lines, like if you looked in one direction, won't do as well as other lines. But overall, this would be the best shape because the point that's like lying, let's say this is the single point down to here, that would be this residual. And so you say, okay, how well does this one point in this part right here, this residual, that's how we judge it. And this 1 point's residual might look really off in one dimension, but really good at another dimension. But what we really care about is it overall. Okay, that's kind of like me kind of tying like why we can do linear regression and what this looks like. Will you actually need to care about it being in like higher dimensional space? Not really, like not for linear regression. But I think it's a useful thing to know is that essentially if it sounds really scary, it's just breaking it down each part. Okay. So one thing we haven't talked about though, because we were looking at just a simple 2D plot, is using categorical variables. So some variables might just only have a yes or no. So I think I showed you guys before with like, it was the diabetes data set. It was either male or female. Well, those are really categorical. Those wouldn't make sense to be an actual number because remember, we're plotting it on like a number line here. So you'd want to consider, it's like, well, how do we plot that out? So one thing we do is basically something, let's see if I have this right. Okay, so we can do some extra things called like dummy variables. So we can transform these variables into something that's more numeric from the category. So I have this example data here. So this is actually, I think from the curriculum, this auto MPG. And you can see here these different features, this MPG, I think MPG is actually their target. Cylinders, displacement, horsepower, weight, acceleration, model, and origin. So immediately, there's some things in here that might make more sense as category. So for example, weight probably makes sense to be continuous because it can vary for many different things. But from this set of data, just basically look at the first few lines of data. What things stick out to you as a categorical feature?
Origin.
Origin, right? Probably origin because maybe like one, right? And origin also, if you did the data set too, origin is supposed to be like where it is from, which would mean more categorical, right? It wouldn't be a continuous feature. So good. Any other ones that we might see that might be more categorical?
The cylinders.
Cylinders, good. That's a tricky one too, because especially if you're not familiar with cars, you might consider like, if you know anything about cars, you might say, oh, cylinders can range from like, 0 to like 500, right? And you're like, oh, that's just like the number of cylinders or something, like whatever it is. But if you do know something about cars with your domain knowledge, you have to realize, oh, an 8-cylinder is different from a 4-cylinder. And then you'll see here, I think there's even a 6-cylinder, some other ones too. So those are different types of cars. So really, even though they are numeric, you really should think of them as categorical. Cool. Anything else that you guys might think?
The model year too is the same.
Yeah, model year, same thing. So model year is an interesting one. So model year can actually, depending on how you view it, you might actually reason it as a numeric or as a category. This case, I would actually say it's a category because it does make more sense for, like, when you think of what a car is, if the model is really saying what kind of type of car it is. However, you could potentially reason it as saying how old the car is. Maybe that is a feature. And if it's talking about how old it is, that might make more sense to say continuous. So it depends again, exactly how you want to view it. And that's the fuzziness of, like, what makes most sense. And this is usually what I think a lot of people have the hardest part of saying, what is a categorical variable? It's like, well, that's kind of tough to say. So here's some kind of ways you can approach it. So one is just to realize when to use a categorical variable. So first, like we just did, was look at the data. You basically part of your exploration. So one thing you can do, as well as doing the actual head, is do like info and also do .describe. And you can see here, all of these are some kind of numeric. And a float, so a floating point number or an integer. But you can see here, right, immediately there's an object, which means a string, right? Which kind of makes sense. Yeah, car name should be category. It's a different, like, you might have a different category for every single car, but it doesn't make sense to have that as a continuous variable. It wouldn't make sense that a Chevrolet, Chevy, Malibu is different from an AMC Rebel SST. Like, those don't have a spectrum of, like, oh, well, if you increase by 3, you get a AMC Rebel SST. Doesn't really make sense. So that's your first clue. So I would say the first thing you do is see, is there any things that are strings, essentially objects in your data set? And if those are strings, you might want to check them out. Say, maybe that needs to be a category. But from here, you can't really see much. So the other part is going to do describe. So if you didn't know what cylinders were, for example, you might say, I don't know what that is. And you might actually look at some different parts. So one, like, you'll see like weight, which we know, tell you right now, it's not a category, right? So you can see basically it has how many there are here, but the important part is maybe see standard deviation and then seeing a distribution here. So you can see 16, 1,613 is the minimum, 25% is here, 50% is here. It seems to be varying pretty much. And then you can see the maximum. So it seems to have a good, like, change in, like, the numbers and stuff like this. However, if you look at something like cylinders, you can see the minimum is 3, then 25% is 4, 75% is 8, and then max is 8. So that seems to suggest is, like, there doesn't seem, especially these zeros right here, it seems likely, and especially because it's an integer, like this guy, it seems like that's more likely to be an actual, what's it called, category. Now, I might not be completely sure yet. I might still have to do some plotting and kind of this, but, like, I'm saying, okay, like, I see it not very, very much. It might make sense for this to be more category than a continuous variable. Model year, this is the kind of similar thing. You can see it starts at 70, basically it looks like goes up individually, 79. That one is like, oh yeah, you can kind of see where this goes through. And then origin, like Lauren had said, we can see like the minimum 1, 25, 2, 3. This makes sense, like, oh, this is probably just describing, is it 1, 2, or 3, which is really a category. Okay, so what's nice is that we can actually use a plot to actually kind of explore a little bit more. But before I move on to that, are there any questions on kind of using this as kind of giving you a suggestion of what's a category and what's not? Okay, cool, sound good? All right, so we'll move on to a pair of plots now. And so basically on these guys right here, basically I'm making different subplots. So you can see if I run this guy right here, this is direct, I think this is directly from the curriculum itself, is that the subplot is basically plotting out cylinders, model year, and origin. So just know that essentially what's happening in here, this zip function, have you guys seen zip before yet? Yeah, so this zip right here is basically just combining this list right here, which each of these axes, which is coming from this figure. So I'm kind of gonna walk this through because it's kind of hard to understand exactly at first because this is new to you. Basically, this is creating a plot. And it's saying, okay, you're going to have a plot with 1 row, 3 columns, and then the whole figure itself will be a 12 by 3 units. Okay, so hopefully that kind of makes sense. Oh yeah, 12 by 3. And then what happens here is that it's saving into multiple variables. So I could technically put like this as X, and it will save all the information as X. But since I kind of know what this is going to look like, so if you were to go in here, it would say to return a figure axis, I can actually use a tuple. So this could actually, you'll see this really common. You could also have done it this way, and that would mean the same exact thing. So basically it's saying, it's doing something called unpacking, where it knows this is a tuple that looks like something, comma, something. And so that first thing will be saved in a figure, and the next thing will be axes. So you'll see this really commonly used, especially with plots. But basically, this is the figure that is saying the whole encompassing part. The axes is kind of like this other weird, not to say weird, but like it's another object within the plot itself, like the kind of figure. And it's telling you where you can basically make those different axes. And so basically what's happening here in the zip is it's taking each axis, and basically there's 3 different axes because it made 3 different columns, 3 different, in one row. And so it's basically zipping together the first axis with cylinders, the second axis with model year, and the third axis with origin. That's where xcol and ax, basically xcol is that part right here. AX is going to be that first, second, or third axis. So essentially that zip makes it kind of like these coordinates, like XY coordinates. So with that, then we can actually do our plot. So you can see our data, which is our data frame, right? We actually do dot plot directly. So this is making a scatter plot. In this case, a kind scatter. And you can see we do the X column. And in this case, the Y column is going to be the target, right? Which is just an MPG. And we actually save AX because that's what we have up here. I'm going to say alpha 0.4. So this alpha basically just adjusts the brightness of each individual scatter point plot. So the reason why we will do this, well, let me ask you guys, why might we adjust like the alphas to see how transparent these points are?
Because if they're less transparent, then we know that there's multiple points on that one section.
That's right, yeah. And you can kind of see it on here already, is that if there's really light, you can see that there's only one point, but if there's a bunch of points on top of here. So this is really important. Like if you got rid of alpha, let's say if I do like just 1, it's a lot harder to tell where there's overlap because there's a lot crossing over. And then obviously if I can go really small, you'll see that it's very, very light, and you can see there's a lot more overlap on here. So this might be adjustment to see exactly what's going on. This might help for you to find the right kind of perimeter. Also know this color is just set it to blue. So right now you can see basically we did a scatter plot, and you can see cylinders, model year, origin. The reason why the curriculum chose these ones is because you're trying to see, oh, I think these are, what's it called? Category. And you can see is that usually what you'll see with categories, you'll have much more like defined like lines essentially, versus if I threw in instead here, let's try weight. You'll see weight basically has much more of a continuous structure, versus here, it's very defined. There's some at 3, there's some at 4, there's not in between. Model year also, you can kind of see the same thing, is that the MPG does kind of adjust over time. Now, this is where I say this is kind of tough for you to say which is category, which is not. I could argue, if given the right kind of like circumstance, argue that this is actually a continuous variable, or could be treated as a continuous. Can anyone guess why I might say that, or why I could think that?
You could like put a linear line through.
Yeah, there definitely seems to be
Kind of like going upwards a bit.
Mm-hmm. Yeah, good. Thank you, Lauren. And it looks like they could put a line. It's kind of generally going up, it seems like, right? As we increase the year, MPGs kind of go up. And if you guys know kind of like, you're like, a little bit of history, kind of like, yeah, that kind of makes sense. Like cars efficiencies have been improved. There are new regulations to say only certain cars have to have certain like MPGs and stuff like that. So you would generally see this kind of increasing up. So this could potentially be something where every year does actually matter, versus like saying like, oh, it vary. Now, this is where, for example, cylinders, maybe there's a pattern, maybe there's not, but having only so few groups like this would likely say, this really should be category. Versus weight. Weight's very clearly supposed to be a continuous variable. Okay, cool. Any questions on interpreting these graphs?
I had a quick question real quick.
Yeah, go ahead.
Mm-hmm. For model year, I was kind of following along with what you said, and I was just wanted to know if like another way of looking at it is there's a lot, especially when compared to the cylinders graph, there's a lot less obvious grouping with model year. There's a lot more I mean, if we want to talk about it in colors, there's a lot more light blue and not really any dark blue. Is that kind of another indicator, like the wider range of grouping
Oh yeah,
point to a continuous variable?
oh yeah, definitely. In that case, you have a lot less like variance within each individual group, and that's actually what it's funny you brought this up. This is actually a great time to say you can do something like a box plot, and so you can see a box plot. Oh no, is it box plot? Box plot.
Is it just box?
I think it is like box.
Box.
No,
Nope, sorry.
that's all right. Well, you can do box plots. I don't usually do it from this way. Usually, let's see your kind. High density bar box. It should be box. Oh, I think. What's my error going? My type error. Is it because of weight? Sorry, everyone. Oh, alpha. That's why alpha should be included. There we go. Because there's no alpha for box plots. Box plots could be useful in this case, but you can see here it doesn't help us directly because like it just shows the distribution. This is where you might use a box plot if you imagine each individual part actually being, I think actually, this should be switched. Anyway, you could use box plots, and I'll show this a little bit later on, but you could use a box plot to actually look at the distribution for each individual group and see those parts. Usually, to be quite honest, I usually like to use Seaborn for those kind of things. It's a little easier. So this is kind of cool. It's like, okay, if you have an idea, one way you can do this is what I like to do is using pair plots with Seaborn, which is SNS. And so basically it will plot every attribute against each other. So let's see if I can do this real quick. Here we go. So there we go. So this is a really useful thing, is that it's a very quick way for us to look at what's going on. Now, one thing to note is that basically this is going to plot every aspect to everyone, which isn't quite what we want here. We actually want to talk about the target, but this will be useful for finding correlations. For example, is if you, for example, see, I don't know if you can see this well, but MPG versus weight, you can see there's a correlation here. You can see, like, let's say weight and horsepower. You can see there's a correlation in that case too. So this kind of gives you a good picture. And then in the middle here is actually the distribution of the different like variables. So for example, if I look at here as cylinders, you can very quickly see, oh, most of them are basically very punctuated, where all of them are, like in this case, I think it's like 4 cylinders, and then I think there's 6 cylinders and 8 cylinders after that. And so this kind of gives you a lot of information very quickly. If we wanted to look at these specific ones, MPG and cylinders, for example, we just look for MPG in this case, which is on the top here. And if I kind of scroll up here, you can see, for example, this is the cylinders plot, so you can have this immediately. And you can see very quickly off here, it's like, oh, well, this is clearly category. This one looks very much like a category. If I scroll down now, we can see that's origin. So this is a very quick way for us to like plot out many aspects. And it's a good like explore. I think it's a good explore feature where you're just like, give me a bunch of information. And there's a whole bunch of things. We see distributions, we can see relationships, we can see correlations. Okay. So again, useful guy. You can also do like, there's a whole bunch of options in here. You could select specific categories, certain features, so you don't have to plot everything out too. If you have too many features, note that your computer is going to have a hard time doing it. So later on, when you actually do something transforming it with dummy variables, I would say don't do a pair plot after you do dummy variables, because basically with dummy variables, you'll have like more features, and this will actually get very large, and the computer has to plot out each point, and I have a lot of people whose computer just hangs afterwards, and it makes the graphs super small, so it's not easy for you to read it anyway. So yeah, but anyway, super useful. And so this one right here, this is GCA, get current access. Okay, so this is another way we can just do histograms. So you can see here is we can make these nice histograms, for example, what's it called, on each part. So you can see here basically the distribution. So you can see this is acceleration, cylinders, displacement. That's essentially what's going on in this diagonal up here from the pair plots. So you can very quickly see if there's a nice spread of information, if it's uniform or if it's punctuated, like these cylinders and origin. Usually if you see things like this, this usually suggests that these should be category. You can also see like model year seems to be punctuated on these parts right here. So that might be interesting to know. It's like, like that might be something like, why is it at this point? That might be something that interesting to say, like, well, why exactly has it been together? That might just be pure chance. Maybe, for example, if I saw, well, let me kind of give a scenario. It's that if you saw this graph and it went from like 1970 to 2000, and you saw it at 70, and then 80, and then at 90, and then at 2000, those punctuated points, what do you think the reason that would happen? Is it because there's more cars in the 80s and the 90s and stuff, or is it something else? Hypothetically.
Like the full 10-year period.
Say that like
the full 10-year period, right? So it'd be like these are all that, like from the 90s, and these were all from the 80s.
Yeah, good. Okay, I want to make sure you got that. Thank you.
Okay.
Yeah. So, and Rebecca, did you have something to add on to that?
I was just wondering if there were times where, because of spikes, increasing energy savings. So maybe those are times of the energy crisis where there was an emphasis on models on cars that saved energy or that had high gas mileage.
It could be. And that's something you should be always really aware of as you're looking at a lot of graphs, a lot of data. Remember that this thing is only showing what cars there are, just the number of cars, not the actual MPG, how well they do. So this could be completely unrelated.
So the y-axis is, not there.
It's not just the frequency.
Okay. It's not the actual correlation. Yeah, okay.
Right, and that's why always be.
Yeah, go ahead.
Yeah. No, and that's where always be kind of aware. Like it happens sometimes when you're looking at graphs. Sometimes, especially if you're looking at many graphs, over long periods of times, it can sometimes like mix a little bit, and you start seeing things that, or like interpret the graph that's not quite exactly right.
Well, I wish they would put I wish to label, like a lot of times in the Jupyter notebooks, the y-axes are not labeled, and that's kind of frustrating because it's like when you actually go to present, you always have to have labels. It doesn't matter. X or Y, you have to have them. And they don't always.
And that's a good point, is that these would not be things you could present directly, is that these should really be seen more as exploratory, where you're running that specific one and seeing, like, you should know when you're getting this, that you're doing a histogram.
Right,
so
right,
that,
I understand. Yeah, but I'm just saying, given that this is given towards students to learn from, it's a professional product. I'm just saying, like, the fact that it doesn't even come out that way with its y-axis plotted, sort of like to say number, and that would be helpful, right? Then
I think I get what you're saying. I think like if you're using this as a learning thing, like saying, as you trying to figure out what's going on here, definitely it's useful. Like whenever you're talking to someone else, like essentially that's what the curriculum is doing. It's talking to you. You want to make sure you have that, like, make it clearly defined. However, if this is more of like, what would you do as a data scientist, like writing this code, it's just already written for you. But if you were like writing this code, you likely wouldn't put in the extra time to put the x-axis and y-axis, because you kind of already know what it is. So you can just do it for a quick explanatory stuff. Then you write your notes. Like, for example, if I were to find this right here, I would, made it too small. If I made a new cell underneath there now, I might say, okay, like if I do like a markdown cell, it's like, like histograms show origin. And this would be a quick note for myself, like origin, model year are likely, category, right? So I might do something like that. And that's where like you want to make sure you keep track of what you're doing versus, because again, you won't be looking at these graphs all the time it's going through. But good point though, especially if you're talking about presenting to someone else. But at least for explanatory variables, when you're first doing it, you just want to do a quick dirty graph to say, all right, let me just see what's there and move on to the next part. Okay, but good point, you wouldn't show this.
Victor, what would you do, like, since you're unsure about model year, what would be like kind of the steps that you would take? Would you go back to the source of the data?
Oh yeah, you're saying like, why is it this way, right?
Yeah, like just to clarify it, if you can't figure it out, like, because I feel like we're still kind of on the fence about model year, or am I wrong? Are we?
No, I think you're right, is that you probably would be like, I'm not sure exactly, like if I saw an interesting pattern like this, it might just be pure chance. It might be the way it's been. What I might do is do a scatter plot, like look closer at something like this. And I might say, there seems to be, like if I were to adjust this like back to like about 0.3, there seems to be, like, I can't directly see on this part. I might actually explore saying, what's the distribution? How many are actually in these different parts? Maybe I go back to the source. So for example, this is where you go maybe too deep into finding patterns that don't actually exist. You might say it's 1970, and in 1971, there seems to be a little bit more cars in 1971. And then it goes back down. Like, what was wrong with 1971? It might just be the nature of just how much data you collected. Maybe you just happened to collect more 1971 cars. This is where sometimes you don't have an answer. Sometimes you're just like, there isn't thing. But if you see a really quick thing, you're like, can I explain this right now? Or at least like think about what might be the explanation and try to come up with that part. Now, this is where I'll put a little caveat, is that this is where like the human brain, in a sense, like works against you. Always be aware of like things like your already like way of thinking. So for example, Rebecca kind of showed a great point, is that, sometimes, I think she just, like didn't realize it was on miles per gallon, but you might have something in your mind where you're thinking about just fuel efficiency and stuff like that. It's like, oh, maybe there's more cars because they were more fuel efficient, so they sold them more, or you wrap everything around fuel efficiency. And maybe it's as simple as saying, oh, there were just more cars made that year, and so therefore there were just more in that year. That could possibly be an answer. But in reality, it's like you might just go back to you might go into the data and say, okay, is there other connections? Is there correlations? Is there a way I can explain this? Or just go back to the data set itself, like say where it's collected, and see if you can ask the business, like, hey, like I noticed this interesting pattern, if it is interesting, like in the sense that it sticks out a lot. It's like, what, like, do you have a reason why this might be true? And then I say, oh yeah, we did a big survey, for people who are, at a certain age group. So it makes sense that they would have this age car or something like that. They might be able to tell you. This is where it's always good communication between where you get the data set and you actually doing stuff with it.
Are these all the same manufacturer?
No, I think in this case, it's not the same manufacturer.
Okay.
I think because we saw like, was it like Chevrolet, Buick?
Oh, okay. Right.
Mhm.
Okay. Yeah.
And this is where I like to say, like, it's really easy to get stuck in the weeds. Like, because all of you all are probably like more analytically minded. You're going to try to find patterns. You're going to try to pull out each part. And this is where it's always important to kind of like have your, like, I said, like your guiding star, your North Star, saying like, all right, what direction am I going towards? Like, what is my goal in doing this? And you might put some extra notes and say, this is interesting to come back to, but maybe not focus on it right away. So.
Well, I guess, yeah, you could, I mean, if you dig into that thing, it's like maybe you do a stack bar chart where you identify the different models within each bar, and then see if maybe there was a big seller, like there's something, everybody had to have the Model T, right? Of course that was the first, but everybody had to have whatever, the Camaro, blah, blah, blah. And so maybe they sold a lot, and then that's just how it ended up.
And this is where I will say, like, I wouldn't even go into that far, because what I would do first is do a very initial, like, seeing what the categories are, see what the correlation is, because if I find like,
what the question is you're trying to answer, I think.
Yeah.
Yeah. Right.
Because like, if you go into this part and start digging in, which, it's always the fun part. It's like, oh, like, what's the reason why? Or like, can I split this up and kind of explain it? But then you realize that model year has nothing to do with MPG. You're like, oh,
right.
Well, that was basically a huge sidestep and didn't have to do that.
No, it could be because if it's an 8-cylinder, like, isn't this 8-cylinder less fuel efficient? So if it turns out there's a particular model that was very popular, then, maybe the more were sold in that year. That's all I'm saying. I mean, it's a little bit digging. I mean, it depends on how serious you really want to take this whole thing. But you're right to point it out that it's an interesting distribution.
Yeah, and this is where, like, I like to say, like, I'll point out these things, like, oh, this is interesting, and I'll make a note of it. Because in the real world, including this project, you won't be able to explore everything. There's just not enough time in the world to do all the things that we can do. So you want to basically focus on the things that give you the most bang for your buck. It's like, what are the things that are the most important features that will explain this? And if, like, maybe there is some pattern in here that's really interesting, but if the model year is like relatively small and it relates maybe to like some other aspect, maybe I don't need the model year at all. In that case, like, I could just completely get rid of this and just think of just the cylinders, or just, like the horsepower or origin or something like that. This is where, like, again, I think it's good that we're kind of talking about this, it's kind of going a little off track. It's good to say, oh, don't go into those rabbit holes at first. Definitely go in the broad strokes. It's like, okay, what are my different categories, and then see what we also may want to do is end up seeing what's the correlations and how much do they relate to the actual, what's it called, target. So yeah, but then once you get there, you're like, okay, let me go explore deeper.
Victor, isn't that where subject knowledge really would come into play?
That's true, yes. Domain knowledge is...
Like for instance, with the model year, they don't make major design changes every year. So this could signify when major design changes were made in specific models.
Yeah, so maybe that could be the signal itself. It's like maybe that's why there's a lot of these kind of in the data set itself. So yeah, model, like domain knowledge, that's what we'll kind of usually call it, is that domain knowledge is always going to be super important. And if you don't have that domain knowledge, it's perfectly fine to ask someone else to say, hey, like, can you tell me more about this data set? Or, you know, like ask them, like, I'm not really familiar with this. Like, can you go more or maybe do some research about it? But usually that's a secondary thing once you do the initial, like overall, like exploration. So yeah, all are great points, guys. So cool. All right, so I'm gonna go on into transforming categorical variables. Sound good? All right, cool. So once you identify, it's like, okay, these are categorical variables, we have to actually do something with it because we don't want to treat them as numbers, because it doesn't make sense, for example, origin 1 and 2 and 3, it doesn't make sense to say origin 2 is twice as good or twice as big as like origin 1. It's just kind of a different category. So one thing we can do, and I think this is from the curriculum, there's a label encoding. I think I could be wrong. Basically, we have our D type, right? It's integer 4. We don't want it to be separate by itself. So what we're doing here, we can actually change it as a category. So now if I do this, this will change that data into a categorical variable. And we see here that actually shows now that D type is category. We can now see our cylinders are unique. So in this case, we can actually see how many different categories there are. And note that this does say categories, even though they are integers. So that means Pandas knows now in the data frame, these are categories, these are not continuous variables. In this case too, there's a little more manipulation. We can just kind of check this out. This is basically saying, take the cylinders, the category, and what's the code for each one. So basically you can see here is that because even though it's 8, 4, 6, 3, 5, it's converting it into either a 1, a 2, a 3, a 4, or a 5. That way it's like saying this is category 1, category 2, category 3, category 4, which again, we're not completely done, but it makes it a little cleaner if you have multiple categories.
I had a question about that. Are there three-cylinder engines and 5-cylinder engines? That just seems like weird. That are those real data, or is that like we think mistakes?
It could. So that's something you can say, like if you have domain knowledge, like I see Jeffrey here, it's like yes, definitely.
That's what I'm saying. Yeah.
And this is
domain
where like
that's not right. 3 and 5 oddball.
You might realize like, oh, that's a relatively rare thing, which is why you might see a few of them. For example, you can see for cylinders, there are a few, like maybe around 5. Like there's not 1 or 2.
Plot, you'll see, right? Exactly. There's like 3 there, and there's 3. But I'm just saying, would you clean that? Would you consider that to be? That's just noise, right? So I don't know. I would.
Well, it depends what you mean by noise, because noise doesn't necessarily mean just because things are different from each other doesn't necessarily mean it's an outlier. You should get rid of it. An outlier.
I'm not saying that. I'm just saying because it's not physically possible. Is it physically possible to have 3 and 5-cylinder engines?
Yeah.
If it's not physically possible, then I would say that's probably mistakes of some kind, right?
Yeah, if you knew from your domain knowledge that 3 cylinders did not exist, for sure, you can get rid of it. But if you do know, it's like, oh, 3 cylinders do exist, but maybe they're not as common, then you wouldn't want to just get rid of them just because they're mistakes.
Right.
Also, if they're mistakes, you might want to say, oh, let's figure this out. Let's put these in the proper category if you realize what the mistake likely was. Classic is like if someone put down typed in the number 1 or ONE, or they pressed the keyboard twice. It's like, oh, like they put in like 99 when it should just been 9. You can notice a lot of those things versus just getting rid of the whole data set. Also, even if there's that small number, you might not want to get rid of them because they might be an important category within this part. Maybe 3 cylinders, just making things up. 3 cylinders are really fuel efficient, And so if it's a 3-cylinder car, it's like, oh, like that's actually going to show a huge jump in NPG. So you wouldn't want to just get rid of that because now you have an important part of your data.
I'm just saying in this real case, given the data that we have and what we know today, at least it would be something I would consider. Normally, if I were looking at this at work, I would say, if I know for sure there's no such thing as a 3-cylinder or a 5-cylinder, I would probably just clean it so that the analysis, the signal to noise can raise. I would either take it out since it's only so a few points, given that it's own, it looks like it's maybe less than 10 points total for those two categories. So that would be what I would choose, just because we can leave it in, but it probably doesn't matter either way. You can look at for it either way, but I would.
Yeah, I think actually in this case, there are 3 and 5 cylinders. So in this case, we'll keep it in there, at least for that case. But you might go back to it later and say, maybe we'll remove it because it's muddying up the rest of our data, even though they do exist. Maybe it might not make sense to include it because there's so few points that we can't really get much information from it. But that's something like, this is like the past the exploring kind of place. Like maybe you'll do some cleaning in exploring. You go back and forth between those 2 sections. But yeah, cool. So going back a little bit on transforming it, right, is we'll take our data, we have our code, and then you can basically do a label encoder, which essentially now will make it so each point now will essentially be labeled as those different parts. This is not what you likely would do for actually cleaning up, like for linear regression, for many machine learning models and stuff like this, because again, you still have the issue of saying, well, what's it called? Is this category twice as good as the other one? So what you likely do in this project is actually something called dummy variables. And basically what happens here is you take your original data, and you could actually have done this directly from here, but I think the curriculum kind of shows like to pre-process it. You can do dummy variables straight from here. And basically what you all have to do is from PandaS's get dummies function, and you can call this right here. And basically what happens, it says that each category is category 1, category 2, category 3, so like 8, 6, and 4 cylinders, for example. And it says on each data point, it says, is it a category 1, 2, or 3? 1 meaning yes, it's category 1, 2 meaning no, it's not category, or 0 meaning no, it's not that category, and so on. So you can see here that you will always have only one number on each of these parts, because if it's category 1, it's not going to be category 2, and so on. So this is what we mean by your dummy variables. And so essentially what we're making is a new column for each possible category. And so another way you could have done this, instead of get dummies, sometimes you'll see sklearn, and this is where like sklearn is used more for machine learning stuff. So you might actually see this more commonly, but it does the same exact thing. So the reason why we can do this is, I like to say, is that by doing your categorical variables and saying 0 and 1, what you're really saying is you're making a new like boost and bump. So remember that our line of best fit will look like, oops, let me draw. Come on, draw it there. Our line of best fit will look something like this. And let's say we have a 2-dimension thing, and we'll have a line that goes like this. Okay. And this line, let's say, it's just all encompassed all of these features together. Well, this 0 and 1 basically will have, let's hear, we say y hat is equal to, and we'll have like all the other stuff that we already figured out. So those other features, and then it'll be plus the category variable. So these last ones, like, okay, we'll have like category 1. So like, let's say x1, and then plus some number times category 2, plus category 3. Okay, so what happens here is that if this is 1, right, if x1 is 1, this is 0, this is 0, and that means that basically you're just adding an a to your y hat. Essentially, it'll bump it up, or it could potentially lower it by a if a is negative. So it'll go up by a. If it's category 2, it'll take this line and it'll bump it up only by b. Because essentially, if I have 1 here, or 0 here, it'd be 0 plus b times 1, which is just b, plus 0, plus the rest of the stuff and y hat. And then you can see like c, like let's say c like really bumps it up over here. Okay, and so essentially what happens is that it makes new lines. Like you can imagine, this is a new line here, this is a new line here. And that's what we're doing with categorical variables. Basically, it's like, do you boost it up, boost it down? Now, note that there's kind of a little caveat here. Is like, it's like, okay, I think I can get that. Like if you have like, a certain origin, maybe you already get like, it's like, oh, let's say like Japanese cars tend to be more fuel efficient. It's like, okay, like we'll bump it up by this much, kind of like, because it's a Japanese car, even though everything else is the same. One aspect of this to be careful with is that technically, like you guys might know this already, is that just because you have like one feature, it doesn't mean it's going to go up linearly. It might be an interaction. So for example, if you have a more powerful car, I'm just trying to make something up on the fly, but if you have a more powerful car, and let's say like a lighter car, maybe it's actually more fuel efficient because it's more powerful and like able to be more fuel efficient for lighters. But if you have a powerful car and a heavy car, it would actually be even less fuel efficient. So there's these interacting parts. That's not something we're actually going to worry about right now, but it's something to kind of keep in mind that like those can have interactions and stuff. But for categories and the way we're treating them, they're essentially being independent from each other. So each variable will affect it by itself. Okay, cool. Any questions on transforming these guys? Pretty cool. Okay, so main idea here is that you want to use get dummies to basically convert them. So each column will now be either a 0 or 1. One thing to note too is that in your regression, you'll want to drop one of these categories. And the reason why you'd want to drop one of these categories is because essentially it'll change your y-intercept. So if you do OLS versus sklearn, what you might see for linear regression is that you'll have different equations for the line. And you're like, what is going on? And it's because sometimes the intercept, remember the intercept is like kind of like our baselines. Like if everything is 0, like basically set everything down to the default 0. That's like at the baseline, like miles per gallon. And then everything else kind of adds or subtracts from there. Well, the problem is if you have a category here, like that category C, well, that's essentially like adding a new y-intercept in there. So if we basically, the way you can kind of think about this is if you have category 1, category 2, category 3, do you really need category 3 if you say yes or no for each of them? Not really, because if you know it's not category 1, you know it's not category 2, you know it's got to be category 3. So if these are two zeros, you're basically just repeating the same information. And this leads us into actually multicollinearity, is that you want to make sure that you are counting all the information and not repeating yourself, because you might be boosting the signal essentially. So here we go. So basically multicollinearity is when features are correlated with each other. Essentially like those, like I said, those categories, those are related to each other, right? If you have one or the other. So regression relies on the fact that they have to be independent, at least linear regression, the way we're doing it. So when you change, basically if you change one feature, you can expect an outcome to go up. It shouldn't be that you have to change 2 features and also you get a huge boost, okay? Because then they wouldn't be independent. So large changes in like the prediction model, what's it called? I don't know what I'm writing here. Ignore this for now. Because maybe inaccurate. Oh, it's saying, okay, I realize what I'm writing now here, is that if things are multicollinearity, if they are correlated with each other, what might happen is that very small changes in one variable, because they're basically boosting each other. If like, let's say weight and horsepower are related to each other in a really strong way, is that if I increase one, it's actually technically increasing the other one. So you'll see a larger change than you should in the model. Also your p-values for your linear regression analysis will actually be probably inaccurate, because what you'll see is a very low p-value for one and maybe a high p-value for the other one, or both low p-values. It's hard to tell because that p-value is being split up essentially among 2 of those. This is kind of like not exactly mathematically correct, but you can kind of think of like that p-value is being shared amongst 2 different features, and it's going to basically affect that part. There's other ways to deal with multicollinearity that we're not going to go into right now, just because they're, what's it called? There are more advanced ways to kind of deal with it. This is always a huge problem. The simplest way essentially is just to drop it. That's kind of like the straight up like, oh, if they're correlated with each other, basically it means that you have one feature that's more, explains the other feature, then you don't need the other feature. You would go ahead and drop that. There's more advanced ways you could do this. For example, something called PCA can be a good example of this, but they're a little more advanced that we don't have to worry about, at least for right now. Okay, so some examples of multicollinearity is one thing is, like I said, you can just drop it. Or sorry, no, you're dropping this part so we can actually see all the features by itself. So this is from the curriculum. So you can see here, we're just looking at those features, the strict data, and then we can do a scatter matrix. So a scatter matrix will kind of look like a pair plot. Is that essentially what we're doing is we're trying to see what things are correlated with each other. So you can see here is basically you're looking to see what things have positive or negative correlations. And you can kind of quickly see is that what you want with no correlation is something like this, where it's a little more like fuzzy. If you have something that's really well defined, for example, like this like horsepower and displacement, you can see there's a very strong correlation here. basically you're counting for the same variable. So this is something that you don't want to include in your model, because essentially you'll get those issues where you're basically double counting. So if you're looking at this correlation, then one thing you can do is, like, this is a very quick way we can like see if there is correlation between the two visually. And then you can say pretty quickly, it's like, okay, it looks like horsepower and displacement have a strong correlation, maybe weight and horsepower too. Those could be correlated together. It's not as strong. We also have acceleration and horsepower. It's a little less correlated. It's a little more fuzzy. It's a negative correlation. So maybe that's not something we have to worry about too much. And I see the same thing with displacement. It's like, it's kind of there, but not super strong. So maybe that's something we don't have to worry about. We can actually do this. We can actually calculate Pearson's R for correlation and actually make a matrix. Essentially, this is the numeric matrix of this. So you can see displacement on displacement. These are all 1 because they're correlated with it themselves, right? So of course they're going to be 1. But you can see here, for example, displacement horsepower. That's a very strong correlation, about 0.9 for Pearson's R. So this means that this is likely very closely related. So I might actually want to consider dropping one of these, one of these columns. And then you can see here, like I said about like acceleration and weight, you'll see acceleration and weight right here. It's like there's some correlation, but it's definitely not super strong. It's only 0.4. Usually the general rule, it depends on the application, but after like 0.8, like a Pearson's R of 0.8, that's a really suggestive of high correlation. Maybe 0.7, depending how, like, honestly, like, especially if you can like reason, say, oh, these would be correlated together, and you see a 0.7 correlation, it might be a good idea to consider dropping those. Note, however, that by dropping data, you do by its nature remove the predictability from a linear regression, because essentially what you're doing is you're getting rid of data, which means you're getting rid of more explainability from your model. So essentially is that maybe, like, even though this is like really correlated, this horsepower and displacement, if I dropped horsepower, maybe horsepower did have some aspect that did help explain the MPG beyond just displacement, because it's not perfectly correlated. There is some information and there's some fuzziness. But in this case, we would probably reason there's so much correlation in there that it would be hard to use that information usefully. Basically, the correlation, the multilinearity is going to be a more overpowering effect than us getting any useful information. And just note that technically, like, you'll always see some correlations. You'll rarely see a correlation of 0 with most things, because if these features are explaining the MPG, they should be correlated with MPG, right? But if they're correlated with MPG and other features are correlated with MPG, then those might be correlated with each other at some level as well. So you'll never have like a perfect 0 correlation, because otherwise it's just random, which probably means they're not explaining your target anyway. So just kind of be aware that a little correlation is fine. You just have to decide when is it like too much. Basically, when is it going to be boosted the signal a little too much? Okay. Cool. And then you can see here, you can also do a heat map, which again is just another visual way of representing these numbers. So essentially you can see here is that these 0.9. I tend not to use these ones because I feel like it's just as easy just to look at the numbers. Like, I would rather, personally, I'd rather like printing this out because I can very quickly see those correlations and what that fuzziness looks like, and then numerically confirming about whether I should drop it or not. Okay. Any questions on those guys? Okay, cool. Multicollinearity is probably like the big one where I think people kind of get stuck on and be like, what is too correlated together? There isn't a hard and fast rule. Generally, I hear like 0.75, 0.7 even is too correlated, and that's when you should consider, well, in this case, our fixes are dropping. But in more advanced scenarios, you might do something called PCA, principal component analysis, where essentially you draw new lines. Essentially, you make new features from the other features, you make like a super feature, and you hopefully are trying to get more information, and you would drop basically the new super feature that has the least amount of information in it. And that's essentially pulling in the parts that are correlated together. But that's a more advanced topic, which we will talk about eventually. But not for this project. It's already a lot for you guys to take in. Okay. Yeah, so I see we only have about a minute left. So I do have a thing on feature scaling. I think this is actually the empty one. Yeah. So I do have one in there. I think I need to update the repo. But the rest of the stuff that we talked about should be on the repo now. I think what I'll do is our first office hours on Tuesday, I'll talk about the other aspects of feature scaling, cross-validation, and such. I know we kind of talked about doing a walkthrough for Project 7. So obviously that's not gonna happen right now in the next like 30 seconds. But maybe this might be something if you guys want to pair up. If you guys would still like me to walk through it on maybe on office hours and stuff like that, put that on Slack. Maybe I'll send a little poll and say, what do you guys want to talk about these next few office hours next week? I'll put that out by the end of today. So that way you guys can vote on there and I can kind of prep some stuff. Or, you know, if you want to make sure, I would say still reserve maybe like Wednesday, for example, let's make sure there's just purely question day. So you guys can ask questions about your stuff. But yeah, cool. So I guess I'll go ahead and stop recording here if you guys are all cool with that.